Good morning, students. Today we are going to discuss very important topic from chapter 4, and the chapter 4 is your moving charges and magnetism. The topic which you are going to discuss is your charged particle moving in a uniform magnetic field. Now, here we are going to consider two cases. Number one is your charged particle moves at right angle to the magnetic field. And the second one which we are going to discuss is your charged particle moves at an angle to the magnetic field. So let me start with the topic 1, that is your charged particle moves at right angle to the magnetic field. Now you see here in the diagram, let me explain the diagram first of all. Now some cross mark we have given, and this cross mark basically define magnetic field. Now, as you have written here, the magnetic field is perpendicular into the plane. So, if you have to symbolize magnetic field perpendicular into the plane, then what you have to use the symbol? The symbol is your cross. Now, if I give dot to represent the magnetic field, that dot represents the magnetic field perpendicular out of the plane. So, here we are considering the magnetic field is perpendicular into the plane. Now on the plane there is a charged particle plus q charge and it moves perpendicular to the magnetic field, because magnetic field is perpendicular to the plane and the charged particle is on the plane. So charged particle moves at right angle to the magnetic field. So as the charged particle is moving and the charged particle is in positive in nature, so it is the motion or the direction of velocity of the charged particle is nothing but the direction of current. So you can use Fleming's left hand rule. Now if you stretch your three finger, one is your first finger, another one is your central finger, and another one is your thumb, in such a way such that they are mutually perpendicular to each other, and if you point first finger along the direction of the magnetic field, that is perpendicular into the plane, and if you consider the current is along the direction of velocity, because the charged particle is positive in nature, then definitely you will get the direction of the force towards the center, as we have drawn a circle. Okay, now as the charged particle is moving, so at every point you can define the direction. So at every point you will see that the direction of force is along the or is towards the center. So what happened basically, due to this force, the charged particle will describe a circular path. Okay, because what happened, a circular path comes out whenever there is a force perpendicular to the direction of velocity. Okay, so as the force is perpendicular to the direction of velocity and the force is along a particular direction, or you can say it is towards the center of the circular path, which describes by the charged particle, so definitely a centripetal force comes out. Now the expression for the force already we have defined in our previous class, that is your F vector equal to Q V vector cross B vector, and the second point, B vector is perpendicular into the plane. Now as V vector and B vector are mutually perpendicular to each other, because we are applying Fleming's left hand rule, so F QVB sine 90 degree, so the force is your QVB. So basically the magnetic field tries to describe the path of the charged particle in circular nature. So as we have written, as the magnetic field tends the charged particle in circular path, so definitely a centripetal force comes out, and that centripetal force balances by that magnetic force. So centripetal force expression already we know, mv square by r, and r is the radius of the circular path, and the magnetic force is your qvb. So from this expression we can define the radius of the circular path. So radius depends on mass of the charged particle, velocity of the charged particle, charge of the charged particle, and the magnetic field. So if the mass is high, and velocity is high, so definitely it will impact on the radius or the nature of the or the dimension of the path. Similarly, it affects the dimension of the path if the charge and magnetic field changes. So you see, the radius of the path discussed by the charged particle can be defined by this expression R equal to mv by qb, and we have simplified this expression. Now as the particle is moving in a circular path, so few terms comes out. One is your time period. Now time period is nothing but the circumference. If our radius is r, capital R, so circumference will be your 2 pi r. So 2 pi r by v. We have used the relation distance equal to speed into time. So from previous one you can get r by v. So if you take r by v from previous expression, then you will get 2 pi m by qb. So this is the expression for the time period. Now as you are getting the expression for the time period, so you will get frequency, and the frequency is your n equal to 1 by t. So it is the reciprocal, that is your qb by 2 pi m, and the kinetic energy is your half mv square. So again you can use the expression for v from here. V is your r qb by m. So r qb by m you can substitute and you can simplify. The kinetic energy comes out to be your half r square q square b square by m. So you see this expression which you are getting here under the condition that velocity is perpendicular to the magnetic field. Okay, velocity is perpendicular to the magnetic field. Now the next topic which you are going to discuss is your charged particle moves at an angle to the magnetic field. It is neither it is perpendicular nor it is any other angle, but an arbitrary angle theta. Suppose the charged particle moves with velocity v at an angle theta with the magnetic field, and the magnetic field is along x-axis. So v has two components. One is your v cos theta, another one is your v sin theta. Now you see, if you see the expression or if you see the figure, here v sin theta is perpendicular to v vector, no? So whatever expression we are getting here, under the condition that magnetic field is perpendicular to the velocity, is not it? So all the expression we can define it here under the condition that instead of v we have to consider v sin theta, because v sin theta is perpendicular to v. So this expression qvb equal to mv square by r. So here in place of v we are substituting v sin theta, because in this expression v is perpendicular to b, but in this expression instead of v it is v sin theta which is perpendicular to b. So q v sin theta b m v sin theta whole square by capital R. So R is the mean radius, you can say. So you see the path, basically the v sin theta components, what it tries to do, it tries to make the path circular, but there is another component v cos theta on which there is no effect on magnetic field. So that's why the path is no longer circular, rather some linear movement is also there with circular movement, and this kind of movement describes a special kind of path that is known as helical, helix or helical in nature. So you see, if the charged particle is at an angle theta with the magnetic field, then v sin theta will try to maintain the circular path, because v sin theta is perpendicular to b, but the v cos theta will drag the circle towards x-axis. So it is no longer a circular path, rather it is an helical in nature. And all the expression which we are getting here, we can get here by substituting v. In place of v we have to substitute v sin theta, because here v is perpendicular to b and here v sin theta is perpendicular to b. So r is the mean radius of this helical path. So mv sin theta by qb. Now time period, again we can get from here 2 pi r by v. So here what we have to do, 2 pi r by v sin theta. Instead of v we have to use v sin theta. So r by v sin theta you can get from here r by v sin theta, that is m by qb. So 2 pi m by qb. So you see the time period expression is same, that is here 2 pi m by qb, and here is also we are getting 2 pi m by qb. So frequency expression is also identical, that is your 1 by t, that is your qb by 2 pi m, and kinetic energy expression in place of v we have to substitute v sin theta. So here is your v sin v square, v sin theta expression you can get from here, that is your r qb by m. So it is your r square q square b square by m, because m square and m cancel out. So this is the kinetic energy, but here one extra term we will get, that is your pitch. Pitch is nothing but the linear movement described by the charge particle during one complete rotation of the circular movement. So one complete rotation of the circular movement is your time period capital T, and the velocity that drags the path along x-axis is your v cos theta. So v cos theta t gives you the pitch. Pitch is nothing but the linear distance. So v cos theta in place of t, we are going to substitute 2 pi m by qb. So these are the expression which we are discuss here. So please check it out, and one term let me try to define, the helical. When a charged particle moves at an angle to the magnetic field, the path followed by it is a helix or helical. So this kind of path is known as a helical path, or you can say helix. So this is all about. Please go through this topic. This topic is very important for numerical as well as for theory portion. So numerical you will get, and you have to use this expression. So all the expression provided to you, all the values provided except one. So that one you have to find it. So this is all about. Please go through and find out your doubts, and thank you.